Okay, now we want to introduce theorem 3.34, which is properties of congruence modulo. So here we have let n be a natural number and let a be c and d be integers. If a is congruent to b mod n and c is congruent to d mod n, then you can add both equations to each other, you can multiply both equations to each other, and then a to the for each m, a to the power of m is congruent to b to the power of m. So I'll prove number 2 right here, and then proof of 1 will be the next progress check. So let n be a natural number, let a, b, c, d be integers. Assume that a is congruent to b mod n and that c is congruent to d mod n. So here's an example of proof where your assumption is more than one sentence, and that's okay as long as you use keywords like assume or let. So this means that n divides a minus b and that n divides c minus d, hence there exist integers q and k, such that this is true and that is true. Okay, now we broke down the definitions, so then what we're being asked to do is look at a times c and b times d. So we can write a equals b plus nk and c equals d plus nk and obtain, yikes, typo, equals ac equals b plus nk times d plus nk, and then expand it, and then factor an n out of things that you can factor an n out, and then by subtracting bd. Now here's an example of when you do something strange, so you might not, that a reader might not see coming. It's good to use words, and so we use some words here to say we're going to do something strange. We're going to subtract bd from both sides, and we get this guy. And then since that's the thing inside the parentheses is an integer, this proves that n divides that, hence we conclude that this is true. That completes the proof of item 2. All right, now proof item 1. So the proof goes similarly. So did I give enough room for this? Thank you. Good. Proof. So we'll let a, b, c. No, I need to let n be an integer first. Let n, I'm going to use shorthand, be a natural number, and a, b, c, d be elements of the integers, such that a is congruent to b mod n and c is congruent to d mod n. Now notice I did my proof in one sentence. They're both fine. How the book did it and how I did it are both fine. Okay, so we need to unpack the definition because we don't know how to do algebra with the modulo sign yet. That's what we're trying to prove, but we do know how to do algebra with the equal sign. So change our modulo equivalences into equal signs. So then, and it's okay with you, I'm going to do the unpacking the definition with the double whammy. So then there exists, m and k in the integers such that a minus b equals nm and c minus d equals nk. Then, I'm feeling boring. Then a equals b plus nm and c equals d plus nk. Adding these together gives us a plus c equals b plus d plus nm plus nk equals b plus d plus n times m plus k. Subtracting, so again, keeping the reader informed, subtracting b plus d from both sides. Both sides yields A plus C minus B plus D equals N times M plus K. So it's okay with you guys. I'm gonna repackage the definitions two at one time. Then say thus A plus C is equivalent to B plus D mod N, which completes the proof. All right. So that's that preview activity.